Hi everyone. So thanks for joining this new session and talk from Mr. Joseph Morlier from ISAE-SUPAERO. So please let me say a few words about Joseph. So Joseph is currently covers the position of full professor of aerospace engineering at the Department of Mechanical Engineering at ISAE-SUPAERO, University of Toulouse in France. He earned a PhD degree from University of Bordeaux, France in 2005. He was a visiting researcher at l'IAMA Sino French lab in computer science, automation, and applied mathematics, Beijing in China in summer 2006. Visiting professor at University of Michigan in Ann Arbor, USA in summer 2017 to 2022, and visiting professor at TU Delft in Holland in spring 2022. His research interests are in the field of aerospace systems optimization, and more precisely, his current research is at ISAE-SUPAERO, an institute Clément Ader, so ICA-CNRIS, so research institution in France, focus on structural and multidisciplinary optimization, so surrogate modeling, topology optimization, and eco-design. He is the author of more than 100 scientific publications, including 40 plus journal papers, and currently serves as an associate editor of Nature Scientific Report. He took part in several research projects, including 10 plus industrial projects within Airbus, 4 European projects, Maximus, Next Gen Airliners, Agile 4.0, U Howard, and 1 ANR, French research organization, EcoDD. So, Joseph, the floor is yours. You can now share your screen.
Okay, thank you. So I think you are seeing my screen. So I would like during these 20 minutes to make a short panorama of the engineering design that you can solve with MDO and AI. So a lot of this research have been conducted with ONERA in Toulouse. Okay, and I will focus more in AI for E. So it means for engineering problem, and you will see that all of our methodologies are applied to some engineering problem. So for the MDO part, for me, design is really in the center of this methodology. So it means that at the end you have a technologic product, you have a final design which is optimal, and the second part is that you take into account the interaction between disciplines. And in this step, so when you define the disciplines, it could be analytics, PDE, ODE, experimental result, with or without gradient, and you can substitute each discipline by a surrogate model. And what is important is that you cannot have MDO without MDA. So for me, it's a way to fully automate the design process. So from the physical problem, you obtain a mathematical constraint optimization problem, and you often solve it using gradient. Okay, it means you feed the optimizer with post-optimality studies, and in fact, you may include large number of disciplines, design variable, and constraint if you use a gradient-based method. So if you want a good starting point, you can have a look to the book of Martin Sending and to the book of Kochenderfer, and which has engineering design approach. And you have a lot of AI for engineering hidden inside. Just to finish the introduction, here is a short drawing I've seen in Delft regarding Philip's approach. And at the end, they say combining disciplines provide better solution. And I think this is essential for my talk. So it's a tool results-oriented presentation, and the initial question more than 10 years ago was from an industrial, and he told me, "Oh, Joseph, I have a costly multi-physics simulation chain. Can you give me the optimal design at fixed budget?" And let's say after the weekend, full weekend. If you want to go deeper into the theoretical background, here is a list of the 6 papers that I highlight in this presentation. So we'll start by the new trends, what's new in MDO AI for engineers. And here is the first example, so how to solve large-scale MDO, and it's from Professor John Wang in UCSD. And in fact, here is working a lot in graph theory in order to use reduced to solve smaller and easy optimization problem. And also, he combined the full space method for his robustness and efficiency, and the robustness of reduced space method. And at the end, he reached this kind of a large-scale design for eVTOL design in a big collaborative project in the US. Another example is the Dynamics AI Institute from Professor of Washington, so Steve Brunton and Nathan Kutz. And the goal here is that anyone, anywhere interested in AI for engineer can self-educate. There is no barrier to entry for those who want to learn. And that's the main goal. Right now, open science, open research are capable of giving a lot of free materials for every engineer in the industry. And of course, AI can accelerate CFD. And the example here of Steve Brunton use a reduced order model. And this kind of approach back to the mathematics solved using value decomposition. So you have snapshots, you do a dimensionality reduction through SVD, you do a threshold, and at the end you have the offline basis of mod that you can use for online for reconstruction. Okay, and that's the topic of reduced order modeling for digital twins, for Carnot Cox, Farad in Stanford, etc. And this slide from the MDO lab is a really good one application in aircraft design. And you can have a lot of information in this review, machine learning in aerodynamic shaped optimization. And for me, aerodynamic shaped optimization offer a nice benchmark to test all the methodologies. Okay, so the next part is the surrogate modeling, and I will try to give you an overview of SMT, and just by start by for me, in fact, surrogate is the new abacus that every people in the world CFD, sorry, 3 dynamics. There are a lot of abacus that can be reused in your everyday calculation, right? And all this story started, in fact, in 1951 by the work of Kriging and formalized by Materon in Paris for the geostatistic. And it has been more recently adapted to what is called Gaussian processes, and in 94, right? And here is a small example of how you can use GP in order to extrapolate out. And this question is still open. So qualitative claims such as ML works okay for interpolation, but doesn't work for extrapolation are wrong. And you can have a this paper in the left. So if I have access to this kind of data through the month-wise data of CO2 concentration in the atmosphere in Hawaii, you can definitely use a polynomial in order to model this trend. But you can see that you forget all the local oscillation. So GPs are able to predict and extrapolate the mean in red, but also the variance. And you will see in all the next slide that variance estimation is a real bonus in order to do Bayesian optimization. So from matrix point of view, you have a set of input-outputs data, x and y of x, and you want to predict to x star. So you choose a kernel. That's really important. You construct your covariance matrix and you tune your hyperparameters. So here you have epsilon1 and epsilon2, and then you have directly the analytical expression for the mean and for the variance. And that's really the power of Gaussian process GPs. Of course, it's really important to have a lot of existing kernel depending on your application. In a recent benchmark from Coco from ONERA, more than 50 test cases of different complexity. They told that Maton 5/2 is a good one, but you can definitely cook your own kernel. And for this, you can have a look to the thesis of Duvno. So Gaussian processes are used for so this enables the calculation of the 95% confidence region, and also you have in blue the mean, right? The feed point are given by the black dot, and the true objective function is a black line, right? So here you can see on the left you have low variance, on the right you have high variance. If you have the information with the same point, with also the gradient at the same point, you can see that you the variance. And we use it in a thesis 10 years ago, a bit less. And for example, we develop what is called related GPs. So when you know a priori the information, you give prior information from engineering design to your data. And on the left, you have the results with independent Gaussian process. And on the right, you have you use the information from Y2 that you have between -0.2 and 0.2 in order to diminish largely the variance with respect to independent GPs. So you have variance reduction and better approximation. We do this also for any nonlinear integral derivation. It's possible, and we use it for flight tests in order to predict the loads. And you can see when we take into account this relationship in our Gaussian process, the variance is largely reduced. And we can also detect easily outliers with this. Okay. So surrogate-based optimization is a way to balance exploitation versus exploration, and I will give you some hints about it. So if you have a prediction-based exploration, you focus only on exploitation, and that's called the greedy approach, right? And here you simply optimize over the mean function, and you ignore uncertainties. So in red here you have the next point predicted. You can see you exploit only the model. You can have the inverse, focus only on exploration, and so the error-based exploration simply minimize the maximum standard deviation with a specific domain. So you can see with respect to iteration that you minimize the variance, right? And in fact, what is currently done is a trade-off between exploration and exploitation, sorry. And the next graph is minimizes the lower confidence bound of the objective function, where alpha here in the equation is superior to 0. It's a trade-off parameter. So one well-known common way to do this is to define the improvement, define the probability of improvement here in blue. Here you're searching with the 4 points here to minimize the function in black, so that's the same. And you have the probability of improvement, and we can also define the expected improvement, which is an indicator. So it's the esperance of I with respect to Y, and it helps you to do this trade-off between exploitation and exploration. And through the iteration, you start exploring, and you finish by exploit the model, the surrogate model, to finish to the optimal solution. So it can be viewed as the way to solve the global optimization problem with constraint. So how to build this with ONERA? We did it for a limited budget of function evaluation. We used Bayesian information to detect interesting and promising area. And yes, so it's called SIGO-MO. You can find it in this paper. And in fact, here we change the paradigm of gradient-based optimization to the graph on the left to this new one, which try to search for admissible point first. And once you explore well the domain design, you can exploit the surrogate models, and you can finish by evaluating the current base point. And you can see, so at the end, the only stopping criteria is the max budget. Okay, so we release SMT, so it focuses only on Surrogate Modeling Toolbox. So it's open source. That has been developed by SUPAERO, ONERA, NASA, and Michigan. And I will give you some novelties in SMT right now. So I can skip this one just to go to the comparison of SMT versus scikit-learn, and you can see depending on the size of the problem, the standard error is better accuracy for SMT, and we also perform quickly with respect to time. So that's important to compare with a lot of open source package. So what are the novelties? So if you want to use mixture of expert, you can compare if you put all the experts in once. So that's a good one. If not, you can construct an assembly of local expert. We can also treat the multi-fidelity problem. So let's say, for example, you have lifting line theory, vortex lattice method, and run CFD simulation tools available, and you want to globally explore with the low fidelity and exploit with the high fidelity tool. So here is a small example with a cheap initial DOE in green star. The surrogate model is in orange, and you have the expected improvement in blue, and the expensive DOE are in a black dot. So through the iteration, you can see you started to do exploration, and then you exploit here in order to reach the true optimum, right? So we offer also unconstrained optimization, so efficient global optimization in open source. So you have tutorials, and the novelty that on doing Bayesian optimization with mixed variable types, so continuous, integer, categorical. So one way to do this is continuous relaxation. So categorical variables are replaced by two continuous variables denoted x1 and x2. So for example, if x1 superior to x2, we have the blue color, and if x1 inferior to x2, we have the red color. And here is a small example of a 10-dimensional case. The true model on the left, the surrogate model with initial design of experiment of size 10. So you can see at the beginning, the surrogates are not good, but as you increase up to 100 experiment size, you can see that you perfectly evaluate the surrogate, which is here a bit complicated. So two continuous variables and 10 levels of categorical variables. So that's a nice way to treat this. So I finally go to the application and the way to solve eco-design problem. We want to reach aerospace sustainability, and I will show you two examples, one in aircraft design and in the second one in launcher design. So the first one is on the Dragon project at ONERA, which has really hard constraint in CO2 reduction. So we have these aircraft design tools adapted to Dragon, and we solve this optimization problem. So minimize fuel mass with respect to all these continuous and categorical variable here in order to obtain the final optimal design. Okay. So here is the benchmark of SIGO in blue, which is using dimensionality reduction with respect for the state-of-the-art solver in this kind of problem, NSGA2. So you can see on the right that our two approaches are in average better than NSGA2, and we also converge more rapidly. And at the end, you can reach this kind of new optimal design for this kind of distributed propulsion aircraft, right? The second one is how to do eco-launcher design. So here the objective function, the glow. We have several design variables from propulsion, mass and structure, aerodynamics and trajectory. And at the end, we will evaluate the life cycle assessment of the optimal design, right? So we obtain X star and we do the LCA of X star. And what is interesting here is that early LCA results demonstrate that manufacturing take into account 20% of global warming potential, with respect than less than 1% in aircraft design. So that's a really good point. So it's time to conclude. So in two different European projects, we learn industrial and costly simulation codes without having access to the code in a collaborative project. So it's Agile and Agile 4.0. SMT is a natural framework for Bayesian optimization. You can treat efficient, mixed variable, multi-fidelity, and multi-objective. But of course, if you want to do global constraint optimizer, you can use SIGO-MO and you will have to contact us. And definitely by including eco-design constraint, we can accelerate the path toward greener aerospace vehicles. So just a bonus, so ONERA developed a web application for MDO called WhatsApp. You can use surrogate model inside, and you can have an external access also possible. So thank you And thank you, Laurent, for the invitation.
Okay, so thanks, Joseph, for this presentation. So as you know, Laurent has already switched to the next one because we have this system where we have sessions that can overlap to let attendees finish the session they were listening to. So yeah, now we will transfer some questions that we have received through the feed. So yeah, well, one of them says, so could you comment, so you have talked about gradients optimization separately, and it says surrogate optimization separately. But do you know which is the status of the research on using the uncertainty at the same time as the gradient to predict the best points, the best next points?
Okay. So it's a bit confused for me, this question, but anyway, if you have your simulation tool with a gradient available, if you have HPC, you can definitely use gradient-based optimizer, do some multi-start, and you will have a lot of computation. So what is interesting with Bayesian optimization is that you can have a trade-off between the learning part, so which surrogate and do exploration, and the exploitation part. And what we commonly do is to start with Bayesian optimization to obtain a certain optimal value, a certain zone in the variable design domain, and then we start SN up gradient-based optimization with this initial point. So here you can have a two-step approach.
Okay, so they are done sequentially, not using both information at the same time, which I think that was
it exists parallelized Bayesian optimization. So in SMT you can have QAI, which is a way to do this, but it's rapidly growing in scientific application right now.
Okay. Then, yeah, we'll do just a second one because probably all the other people are switching to the next one. So you have talked both about probability of improvement and expected improvement. Could you please give a recommendation in which one is better?
Okay, so expected improvement, use probability of improvement. So you can check in our, I think, AST paper with Prof Martins. And here we, depending on the application, you can use WB2, which is also a good way to predict the next point. So it's we have transformed this indicator, and we have the scale version, which offers good results in multimodal test cases. So AI is most used, but you have different indicators that can be computed with the same data.
Okay. Okay, so thanks again, Joseph, for the presentation. And yeah, now, so we will close this one. You should know that the recording will be available on the event website. And now you can switch to the next presentation. So
thank you.
See you all.